Good morning all. This is Ms.JINE Rosy, Assistant Professor in EC Department in S.A.E. Engineering College. In this video, we are going to discuss about linear time invariant system. First, let us see what is linear time invariant system. A system that is linear as well as it is time invariant means then we can say the system is linear time invariant system. So when the system obeys this linearity principle, that is, if any changes that is done at the input of the system, the same change is getting reflected at the output side. That is, both the input and the output is linearly related with each other. So in this equation, we can express the linear relationship among the input and the output of the system. So let us consider this xk of n is the input to the system and output of the system is represented as yk of n. So, if the input to the system is multiplied with a variable ak, the same change has to be reflected in the output side. That is, the output yk of n is multiplied with that corresponding variable ak. So, whatever the changes that we have done in the input side is reflected in the output side. So, we can say the input and output are linearly related with each other. And next, what is a time invariant? So time invariant means if any delay is done to the input side, for example, x of n is the input to the system, and if it is delayed by a time period of n naught, the same delay has to be reflected in the output side, that is y of n minus n naught. So the delay that is reflected in the input has been noted down in the output side also. So we can say the system is time invariant. So any system which obeys this linearity and time invariant is called as linear time invariant system. And next, the impulse response of the system. So let us consider one linear time invariant system. So obviously x of n is the input to the system and y of n is the output of the system. So if the input to the system is the impulse signal, that is del of n, and what is the output of the linear time invariant system if the input is del of n, that is h of n, the output is what? H of n, that is nothing but impulse response of the system. So if the input to the LTI system is the impulse signal, the output is the impulse response. Okay, so next let us see the properties of linear time invariant system. So what are the properties of linear time invariant system? We can classify them as commutative, distributive and associative. Let us see what is commutative property. So if you consider an LTI system with input x of n and the impulse response h of n and the output y of n, as per the commutative property, we can express the system as x of n convolved with h of n is equal to h of n convolved with x of n. And next, let us discuss about the distributive property. So the distributive property, as per the distributive property, the input to the sum of the system is equivalent to the input to the sum of individual system. Next, coming to the associative property. So according to the associative property, the series interconnection of the two systems is equal to the single system. Next, the analysis of LTI system. So this LTI system, we can perform the analysis with the help of the two transforms. One is the discrete time Fourier transform and another one is the Z transform. So if you use the discrete time Fourier transform for the analysis purpose, the system equation can be expressed as y of e power j omega is equivalent to x of e power j omega into h of e power j omega. So what is this h of e power j omega? H of e power j omega is nothing but the frequency response of the system. And suppose if you are doing the analysis with the help of the Z transform, the system equation can be represented as y of z is equal to x of z into h of z. So this h of z can be called as the transfer function or the system function. Now in the next slide we will discuss about what is the causality and stability of an LTI system. So in order to check whether the system is causal, we have to check for these following conditions. So let us discuss what are the conditions for the system to be causal. So what is the first condition mentioned here is the impulse response h of n should be equal to 0 for n less than 0. So if this condition is satisfied, then we can say the system is causal. And we can also check with one more condition, that is if the system should be a causal, if an LTI system should be a causal, when means when the region of convergence, that is this ROC of the system should lie outside the unit circle. Lying outside the unit circle means what? It should lie exterior of the unit circle. So let us recollect the concepts what we have discussed for this causality. So what is the condition for the causality? First let us check with h of n. If h of n is 0 for n less than 0 means it is causal, or else you can check with the poles, that is the region of convergence. So if the region of convergence lies outside the unit circle or the region of convergence is outer of the outermost pole, then also we can say the system is a causal system. Now let us check the condition for the stability. So when the system is stable, so when the ROC of the system includes the unit circle, then we can say the system is stable. And we have one more condition also to be checked. What is that? Is this ROC, that is the poles of the h of z, that is the poles of the system function, should be smaller than 1. So let us recollect what is the condition to be checked for stability. So in order for the system to be stable, the ROC of the system should include the unit circle as well as the poles of the system function should be smaller, that is it should be less than 1. So these are the conditions to check whether the system is a stable one or it is a causal one. Now let us solve some problem for causality and stability. So take down this question. Check for causality and stability of the system, and the system function h of z is represented as 1 divided by 1 by 2 into z inverse plus 1 divided by 1 minus 2 into z inverse, provided that mod z is greater than 0. Okay, so let us see how to solve this problem first. So I will tell the steps to solve this problem and then we will solve this problem. So what is the first step here is, first you have to rearrange the equation into a standard form. So first what you have to do, you have to rearrange the given equation. Then you have to find what is the pole in the system function. That is our second step. And in the third step, you have to plot the pole in the z-axis. So these are the three steps you have to do while solving this problem. So now let us solve this problem. So first says, what is the first step? I said first we have to rearrange the given h of z equation in the standard form. So that is what here it is done. So how to rearrange this given equation in the standard form is, take the z variable outside in the denominator term. So we will be getting z minus 1 by 2, and that z in the denominator will be moving on to the numerator. So you will be getting the first term like this, that is z divided by z minus 1 by 2. Okay, now let us do the same thing for the second term also. Take the z common in the denominator term. So what you will be getting, z minus 2, and the denominator variable z will be moving on to the numerator. So the second term becomes z divided by z minus 2. So that is our first step. So in our first step, what we have done, we have changed the given equation into a standard form. Now the next step, the second step is we have to find out the poles in the system function. So how to pick the poles in the system function? Let us take the denominator terms. Okay, so this is the first term, that is z minus first term present in the denominator, that is z minus 1 by 2. So what is the pole of this term? So the pole for this term is z is equal to 1 by 2. So that is what it is represented over here. And for the second term, so for the second term, what is the pole? So the pole is z is equal to 2. So we have two poles for this system function. What is that? One is z is equal to 2, another one is z is equal to 1 by 2. So all the three steps we have done, and now the thing is we have to plot these poles in the z-axis. Okay, so for plotting the poles, so first let us take the smallest pole. Which is the smallest pole here? So the smallest pole is 1 by 2. So let us mark 1 by 2 over here. And then what is the next pole we have? The next pole is z is equal to 2. So let us check this slide too. So these are the poles, z is equal to 1 by 2 and z is equal to 2. So that is what we have plotted in this z-axis. So 1 by 2 is the pole, one pole, and 2 is the next pole. Okay, now we have to check whether the system is a causal system or it is a stable system. So now it is the time we have to check whether any condition for this ROC is given in the problem. Yeah, it is given. So check out the question. So here it is mentioned as modulus of z is greater than 2. So modulus of z is greater than 2. So here we know these are the poles in this z-axis. One pole is 1 by 2 and another pole is 2. So we know this as per the condition in the problem, modulus of z is greater than 2. So now where will you plot this ROC? Obviously the ROC lies outside this circle of radius 2. Yeah, that is what given in the question also, right? So modulus of z is greater than 2. So obviously this ROC, the region of convergence, lies outside the circle of radius 2. Yes, because in the problem itself the condition is mentioned. Okay, now ROC is outside the circle of radius 2. Now let us check for the stability and causality. We know what is the condition for causality, right? So what is the condition for the causality? So if the system is a causal means, then this region of convergence should lie outer of the outermost pole. Is it lying like that? Yes, because these are the two poles we have. One pole is 1 by 2, another pole is 2. So now the check for the ROC. ROC is lying outside the two poles. So it is the outer of the outermost pole. So now we can say the system is causal because the ROC lies outer of the outermost pole. Next, we have to check for the stability of the system. So how to check whether the system is stable? What is our condition? Our condition is if the system is stable means the ROC should include the unit circle. ROC should include the unit circle. So where the unit circle lies? Unit circle means it lies in between 1 by 2 and 2. So it is lying here only, this place only it lies. So this is the unit circle. So now listen, now look at this ROC. So this ROC lies here, that is outer of the outermost plane. So definitely it doesn't include this unit circle. Yes, so now say whether the system is stable or not. No, it is unstable because it doesn't include this unit circle. Our unit circle lies here, but our ROC is in this position. So the system is an unstable system. So now what you have got? Our system is a causal and unstable system. Right? Okay. So now let us move on to the next slide. Next problem. So what is the next problem? Find out the possible ROCs, check for causality and stability for each case. So the system function is given, h of s is given, but when you look on to the previous problem, the condition for ROC is mentioned, but here in this problem, see the possible ROCs, what they have mentioned, the possible ROCs. So we have to check the stability and causality for all the possible ROCs. Okay, so now we know what are the steps we have to follow to solve this problem. So first let us check whether the given equation is in the standard form. Check on the denominator term, it is z minus 1 by 4 into z plus 1 by 3, z plus 3 by 4. So obviously it is in the standard form, so no need to rearrange this equation, already it is in the standard form. So skip the step number 1. So let us move on to the step number 2, getting the poles from the system function. So what are the poles in the system function? So the poles are z is equal to 1 by 4 and z is equal to minus 3 by 4. Now let us take modulus of z is equal to 1 by 4 and modulus of z is equal to what? 3 by 4. So these are the two poles for the given system function. Now let us plot these poles in our z plane. So the poles are 1 by 4 and this is your 1 by 4 circle, and next pole is 3 by 4 and this is your 3 by 4 circle. Now check for the possible ROCs. How to identify, how to check what are the possible cases of ROCs based upon the poles only. We can check for the 3 possible cases. So what are the 3 possible cases is, one case is we can consider there is ROC lies outside this pole 3 by 4. That is one case. And next case is you consider ROC lies inside the circle of radius 1 by 4. And the last case is that you consider the ROC lies in between 1 by 4 and 3 by 4. Understand? So these are the 3 possible cases for this ROC. Let me repeat this. So what is the first case? What is the first possible ROC case? So first is we are considering this ROC outside the circle 3 by 4. And next case is considering the ROC inside the circle 1 by 4. And the last case is in between this 1 by 4 and 3 by 4. Okay. So now let us check for the causality and stability condition. So what is our first case? So the first case we are considering is modulus of z greater than 3 by 4. So where our ROC lies? Our ROC lies outside this circle of 3 by 4. Why? Because it is mentioned as modulus z is greater than 3 by 4. So for greater than 3 by 4 means obviously it is lying outside the circle of radius 3 by 4. Now let us check for the condition of causality. So what is the condition for causality? So if the system is causal means it should lie outer of the outermost pole. Check whether it is lying outer of the outermost pole. Yes, this is one pole pole 1 by 4 and this is another pole 3 by 4 and the ROC lies outer of these two poles. So we can say the system is a stable one. Okay, now let us check for the stability condition. So what is the stability condition? The ROC should include the unit circle. It should include the unit circle as well as these two poles should be smaller, that is less than 1. Okay, so let us see where our unit circle lies. Okay, so this is the circle of radius 3 by 4. Obviously it should lies here only. So this is the unit circle. So see, our ROC covers this unit circle as well as this pole values, that is 1 by 4 and 3 by 4 is smaller, lesser than 1. So we can say the system is a stable one. So the system with this condition, what condition? Modulus Z greater than 3 by 4 is causal as well as it is what? Stable. Now let us check for the next condition. So what is the next condition we have considered is modulus Z less than 1 by 4. Modulus Z is less than 1 by 4. So this is the 1 by 4 circle. So 1 by 4 modulus Z is less than, right? So obviously the ROC lies inside this circle only. Okay, now as this ROC lies inside the circle of radius 1 by 4, what is the condition of causality? So what is the condition? The condition is the ROC should lies outside the unit circle or it should be lying outside the out of the outermost pole. So out of the outermost pole means obviously it should lie here only, right? But is it lying here? No, it is not lying here. It is lying inside the circle. Inside, it is innermost. So the condition is not satisfied. So we can't say that the system is a causal one. It is a anti-causal system. Now let us check for the stability. So stability means the ROC should cover the unit circle. Is it covering? No, it is lying interior of 1 by 4. It doesn't cover the unit circle. So that condition is also not satisfied. So the system is anti-causal as well as the system is unstable. For this condition, mod Z less than 1 by 4. Okay, now let us move on to the third case. That is, in the third case, I said the ROC is to be considered in between the pole 1 by 4 and 3 by 4. Yeah, so this is our pole 1 by 4 and this is our pole 3 by 4. So ROC lies in between 1 by 4 and 3 by 4. Now check for the causality and stability. You know the condition of causality, right? So causality means the ROC should be lying out of the outermost pole. Is it lying out of the outermost pole? Obviously no. It is in between the two poles. It is in between 1 by 4 pole and 3 by 4 pole. So this causality condition is not satisfied here. So the system is a anti-causal one. Now let us check for the stability. So stability means it should cover the unit circle. Is it covering the unit circle? No, it is in between 1 by 4 and 3 by 4. Obviously 3 by 4 is lesser than 1. So we couldn't say that the system ROC is not in the unit circle. It doesn't cover the unit circle. So the condition for the stability is also not satisfied. So in this case, in the third case, that is the ROC lies in between 1 by 4 and 3 by 4 case also, the system is an anti-causal and an unstable one. Okay, thank you all. We'll continue the impulse response problem in the next session. Thank you.